Okay, let's consider another type of problem with regarding divergence of curl. We're going to ask, is there a potential? And this is a very common question because we like potentials. So notice that if the divergence of a vector field is 0, that actually means it's a curl. It actually means that f is a cross product of g with the gradient. On the other hand, if we know that the curl of f is 0, in other words, that the cross product is 0, we know f looks like a gradient. And so to this end, you can note you can add a couple of heuristics to spot some of these, and notice that it will be antisymmetric. The cross product is antisymmetric, right? A cross B is minus B cross A. And on the other hand, f will look, if it's a gradient, it will look symmetric. So using these heuristics, you can often just spot some of these vanishing divergence or vanishing curl vector fields. So let's do a couple of examples. Is there a G such that the curl of G is this vector field? X, Y, Z minus y to the 7th, z to the 6th. We'll have y to the 6th, z to the 7th. So there's a couple. Let's look at our heuristics. So if we want it to be a curl, that means it should be antisymmetric. So there's two things here because we have 3 components. So I'm going to look at this group first, the second and third component. Notice how antisymmetric these things are. Very good. So we have a minus sign. We also have, and that's the only difference really, because the only other difference is where you put the power. You put it on the y or the z component, depending on which one you differentiated. So that's good. I think this is a good candidate. However, we have this bad term. This is the bad term. Because there is no antisymmetric pair. So there will be no cancellation when you take the divergence. We can't get a plus and then a minus term to cancel each other out. This x, y, z is alone. Notice this is a degree 3 polynomial. This is a degree, what is this? This is a degree 13 polynomial. So certainly these things will not cancel out. So we have no hope. So we're going to conjecture that the divergence of f is not 0. So no G exists. So how do we show this? We're going to compute. So the divergence of f, it's going to be d dx, xyz, plus d dy, minus y to the 7th, z to the 6th, plus d dz, y to the 6th, z to the 7th. Let's do these good terms first because you can see what I mean. So this will give you minus 7 y to the 6th, z to the 6th. This will give you a plus 7 y to the 6th, z to the 6th. These terms actually cancel. So that's good. So we just end up with this first bad term. This is just yz. This is clearly not 0. So like I said, the anti-symmetric terms canceled, but this non-symmetric term, you can't get rid of it. So therefore, there does not exist a G where the curl is f. F is not a curl. It has a non-curly part. So let's do another example where now we're instead looking for a gradient. So is there an f such that the gradient of f is our vector field of the form x, y, z squared, x to the 7th, y, z squared, x to the 7th, y squared, z. Hopefully my z's do not look like 2's. So let's again use our heuristics. And we're going to say look for symmetry of the vector field. And notice we can immediately spot symmetry for these last two components. Notice that they both have x to the 7th. And the y and the z are of degree 3. Right, because it's just yz squared or y squared z, depending on which we differentiated. So therefore we expect the curl to be equal to 0 for these two terms. But however, we have a bad term. This is not symmetric. It does not have other terms that look like it. Right? And one way to see this, this is a degree 4 polynomial, whereas these other ones are degree, what is this, degree 10? Certainly, these will not match, and so there will be no cancellation when you apply the curl operator. So let's check this to see if we're right. In fact, it's enough to show that the curl of this first term, which is just, you put zeros, it's enough to show this is not 0. Right? Because, certainly, the curl of a degree 10 will be degree 9. You'll get some 9th order polynomial. And so it cannot be equal to that. So that would mean the total curl, it'll be something of degree 3 plus something of degree 9 that'll be non-zero, because the c is non-zero. So it does not matter what these terms are. Actually, by the symmetry argument, we think they're 0, but it really doesn't matter. We just need to check the first term. So let's do that. The curl of, what was it? It was xyz squared, 0, 0. Let's just do the determinant. I, j, k, ddx, ddy, ddz, x, y, z squared, 0, 0. So I'm going to expand along this cofactor, which means I'll delete the rows and columns associated with it, so we end up with just this determinant. J, k, ddy, ddz times x, y, z squared. So we get j ddz minus k ddy x, y, z squared. So this should just have j times 2xyz minus k xz squared. Clearly this is non-zero. So therefore, no f exists such that the gradient of that little f equals our vector field. I hope this was helpful. Thanks for watching.